In the next few videos, I just want to give you a couple of more examples of solving differential equations because I think it's a difficult topic for students. And we'll abandon the slope fields for the moment. Hopefully you're able to understand how to create a slope field at this point. But let's just focus our attention on getting down the mechanics of this separation of variables technique. So here's dy dx equals x e to the y. What you want to do is you'll want to separate the dy's and the dx's to get the x's with the dx's and the dy's with the y's. So if you divide both sides by e to the y and multiply both sides by dx, you'll get this. So I might write it like this for this time instead of the division. 1 over y e to the y, or 1 over e to the y times dy is equal to x times dx. And now that you've got your variables separated, you can anti-differentiate both sides. So be very careful. The right side's easy, right? The antiderivative of x is 1/2 x squared. I'm going to put the plus c there. The antiderivative of 1 over e to the y, be careful, that's not ln, because that can be written as e to the negative y. And the antiderivative of e to the negative y is just negative e to the negative y, right? Because e is its own derivative, and then the chain rule would produce that negative, which you'd have to cancel. So this is negative e to the negative y. All right. So I'd write that. So that step, I think you need to reflect. I guarantee some students need to reflect on that. I'm going to write this as negative 1 over e to the y equals 1/2 x squared plus c. Now, one point I want to make here is that you can we've got an initial condition here, right? We've got an initial condition, and you can plug in that initial condition at any time. So you can wait till you've finished finding the general solution and then plug in that initial condition, but you could also do it right now. You could do it right now and find out what that c is, and that might make this process more comfortable for you. So I'll just write when x equals 1, y equals negative ln of 2. And so that means I can write negative 1 over e to the negative ln of 2. And that equals 1/2 1 squared plus c. Now on the left side, e to the negative ln of 2, that's the same as, and again, just up here in this box, I'll give you some scrap work here. E to the negative ln of 2 is the same as e to the ln of 2 to the negative 1 by property of logs. So that just equals 2 to the negative 1, or 1/2. So this denominator here just becomes 1/2. So it's negative 1 over 1/2, and that equals 1/2 plus c. And so that means the left side's really negative 2. So if I subtract a half from both sides, you get negative 5/2. And that means that c is, when you subtract a half from both sides, you get negative 2.5, or write as negative 5/2. So now I kind of pick up from there. Now that I know what my c is, I can put that right here, but I got to continue solving this. So that means I got negative 1 over e to the y equals 1/2 x squared minus 5/2. And now I need to solve for y. So I'm probably going to do a little cross multiplying here. I'm going to view this right side as being over 1, and then I'm going to cross multiply to make this look like negative 1 equals 1/2 x squared minus 5/2 times e to the y. Don't distribute that e to the y because you don't want it to get tangled up with the x's. Divide both sides by 1/2 x squared minus 5/2. So then you get that negative 1 over going to write that as x squared over 2 minus, actually let's just write that as, well, I'll leave it like this for now. And that equals e to the y. I'm going to clean up this left side a little bit, because you can make it look a little better. This is x squared minus 5 all over 2. So negative 1 over x squared minus 5 all over 2 equals e to the y. And now that can be rewritten. This is all just, what I'm doing right now is not, it's all just preference. If you didn't do this, you could still get the right answer. I just want it to look better. That's what e to the y is. Now what you'll need to do is take the natural log of both sides in order to solve for y. So ln of negative 2 over x squared minus 5 is equal to ln of e to the y, which is just y. Alright, so there is our solution to that differential equation. We'll do one more. This is dy dx equals the square root of 1 minus y squared. Y of 0 is 1. Again, I should probably note that we want to find, I didn't note this in the last video, but obviously the directions are to find the particular solution. Alright, that's what we're doing here. So, we'll use separation of variables. Right now, I've got my dy above a dx. I'm going to multiply by dx both sides, and then divide by the square root of 1 minus y squared. So that equals dx. You take the antiderivative of both sides. Now the right side might seem really confusing because it's so simple, but view that as 1 times dx, and the antiderivative of 1 with respect to x is just x. So I'll write x plus c there. The antiderivative of the left side, this is where some of your knowledge has to come into play. That is the antiderivative, or that is the derivative of sine inverse of y. All right. Okay, at this point you can use your initial condition if you want to solve for c. So I'll plug in 0 for x. So when x is 0, y is equal to 1. So that means that sine inverse of 1 equals 0 plus c. And sine inverse of 1, the angle whose sine is 1, is pi over 2. So that means that c is just pi over 2. So we continue the solution here. And if sine inverse of y equals x over 2, then that means that the sine of x over, that the sine of x plus pi over 2 must be y, right, based on inverses. Right? If the sine of this, if the sine of this angle x plus pi over 2 is giving you y, that means that the sine inverse of y is equal to x plus pi over 2. So there's my particular solution. All right, so it's going to take some practice. I think you'll need to look at a bunch of examples of separation of variables, and I think a lot of these problems bring up they'll bring up the whole issue of your algebra skills, right? Because there's a lot of little things here that you need to know how to do and be comfortable doing. Clearing denominators, using laws of exponents and logs, those type of things really come out in the mechanics of solving a differential equation. So just use them as opportunities, or use these problems as opportunities to kind of tidy those things up. Here's another differential equation, and here we're asked to draw the solution curve before we solve the differential equation. So let's do that first. I know it goes through the point 0 pi over 2, so that should be maybe the first thing I plot. And then I know that when I plug in 0, dy dx is 1, so I need to indicate a slope of 1. So that might look something like that. And so what else do I know? I know that as x goes to infinity, that derivative is going to go to 0. So this function should start to flatten out in some sense. And if I go to negative infinity, same thing happens. I don't really know much about the values, so I might just hold off on sketching that for the time being, because I mean we don't know if it's going to dip below the x-axis or not, at least not yet. So let's just, maybe I'll dash it in here. See, maybe it's doing that, right? The slope has to approach 0 because as x goes to negative infinity, that derivative is going to 0. But now let's solve it, and I bet you we'll be able to figure it out after that. So dy dx equals 1 over x squared plus 1, and we'll separate the variables and get everything together. So I'm just going to multiply by dx. I'm going to take the antiderivatives of both sides. The antiderivative of 1 dy is y. The antiderivative of 1 over x squared plus 1, again, this is one thing you'll want to know. That's tan inverse plus c. So this is the graph of tan inverse, which means, well, actually, we have to wait till we plug in the initial condition. So I know when that y is 0, when x is 0, y is pi over 2. So y of 0 equals pi over 2 means that pi over 2 is equal to tan inverse of 0 plus c. Tan inverse of 0 is 0, so pi over 2 equals c. So that means that my function is tan inverse of x plus pi over 2. Now the tan inverse graph usually goes through the origin and has asymptotes, horizontal asymptotes at pi over 2 and negative pi over 2. In this case, we've shifted that graph up by pi over 2, so it has horizontal asymptotes at 0 and at pi.